Welcome to the very first video in the Measure Theoretic Probability video series, and in this video we are going to basically cover just a very brief review of Riemann integration, and then look at some of its deficiencies and then motivation for a new theory of integration. So, in this video, we will do a very, very quick review of Riemann integration with the assumption that you've seen all this stuff once before, because I'm assuming that you've seen all this before, then I will not go over exercises when, discussing this kind of stuff for the sake of speed. So, we will then, after reviewing Riemann integration, proceed to see why this theory of Riemann integration leaves something to be desired and how we might resolve any of the difficulties. Throughout the next several videos, I will repeatedly use a and b as some two real numbers, a less than b, and then this function f defined on the closed interval a to b, and it'll be a real valued function. So in any case, in order not to continually repeat myself, we should just assume throughout the rest of certainly this video and probably some videos into the future that whenever you see a, b, and f, that they, a and b are real numbers and f is this function defined on the closed interval from a to b. So to get started with the quick review, a partition of the interval from a to b is any finite set of values. This is a little bit of an abuse of notation. What we mean is that there is this real number a sub 0, another real number a sub 1. It's a whole bunch of numbers, right? N or n plus 1 different numbers, and they are written in increasing order. And then we form the set of all of these things. So the partition is the set of the things formed like this. So, this is not typically how we use sort of like roster notation to write down a set, but this is just trying to kind of put into a single line the statement that P is the set of these numbers and they are ordered in this way. So in any case, further, we have the condition that a sub 0 is equal to a and a sub n is equal to b. Now, if we suppose that f is bounded and p is a partition of its domain, then for each I from 1 to n, we define this little m sub I to be the infimum of the function that's guaranteed to exist because of the assumption that f is bounded. Oh, I'm missing an equal sign there. So that should be m sub I equals this sup. So we do the same kind of idea for the upper bound, or the sup really. And then we define the delta x sub I as the change in x, so to speak, which is formally defined here. But the point is that we can then, with all of these definitions in place, define the lower sum of f on p. So that is the sum with I, ranging over all of the indices, using those infima times delta x. This should all be very familiar. And so then we can go on to talk about refinement. So if a set P is a partition of the interval from A to B, then a refinement of P is another set P prime, such that the following, okay? There is another partition. This is not always how it's defined, but it makes sense to me. There is another partition Q of the same interval, and P prime is the union of the two partitions. So that is, I think, a good way to think about what a refinement is. Now, a standard thing to prove in the sort of vicinity of these kinds of ideas is that if P is any partition, P prime is any refinement of P, and we assume that F is bounded on this interval so that all of this makes sense, then this chain of inequalities must always hold. So if we take the unrefined lower sum, then that is going to be less than or equal to the refined lower sum. That is always less than or equal to the upper sum, this time on the refined partition. And then the largest is the upper sum on the unrefined partition. But what you should imagine is going on in all of this is that the refinement is always kind of squeezing in. I mean, at the very least, you're never getting farther apart. Refinements tend to bring your lower sum and your upper sum always closer together, closer in than they were before the refinement. That's how you want to imagine that's going. And that's not always true, strictly speaking, but when the function is integrable, then these things do become closer and closer together. So now that we have defined all of these things, we can move on to talking about lower and upper integrals. So the lower integral is, to put it very briefly, the sup over all lower sums. The upper integral is the inf over all upper sums. When both of these exist and are equal to each other, then the shared value is simply called the Riemann integral. And so in this formula here, you see what we mean by the Riemann integral. From there, we can discuss some essential integral theorems, and proving any of the things that we're discussing here, or especially the claims that we are making here, is a good exercise. I don't know if you should necessarily expect to be able to come up with the proof off the top of your head quickly, but certainly thinking about the proof and trying it, and then possibly, if necessary, looking up your old resources on real analysis and seeing the proofs and making sure that you understand them all, that is a good just exercise and self-assessment to see, if you are completely perplexed by all of that, then you may need to brush up on your real analysis. But if understanding it comes somewhat naturally and quickly, then that's probably just a good exercise. But so the theorem, the first essential theorem, is that this is an equivalent condition to Riemann integrability. So a bounded function is Riemann integrable if and only if, for every positive real epsilon, there is a corresponding partition such that the upper and lower sum become close together, right, within a distance of epsilon of each other. The next theorem is even more famous. It is the fundamental theorem of calculus. It says that if you have a function big F that is an antiderivative, then it satisfies this equation, which is, we use it all the time in calculus. So that should be quite familiar too. Now, it is about at this point in the textbook of, not too far from these ideas, that the book gives three motivations for why the Riemann integral isn't doing everything that we want it to do in some sense, and why we would want to look for a different kind of integration. So the first reason they give is scope. They say that there are some functions that are not Riemann integrable, but which we wish we could integrate. Now, okay, I'll complain about this in a minute, but in any case, so then there's the dependence on intervals. So all of this is about integrating functions of a real variable. We've always got our functions defined on intervals, and one way or another, like whether we relax the requirement that they be defined on intervals, or if we relax the requirement that they be defined on real numbers at all, we can't do that with the standard Riemann integral, and so we might want to look for something that is able to handle a kind of generalization a little bit better than the Riemann integral can. And then they, talk about the lack of completeness, which is the idea that if you have a sequence of functions that converge to some particular function, then you would hope that the sequence of corresponding integrals, right? I'm leaving out a lot of the details, and all the details that I'm leaving out are in the textbook, but, you would need that these functions are Riemann integrable. But I'm just being very brief here, and saying that the book claims that we would expect the Riemann integral of each one of the functions in the sequence to then form a sequence of numbers, right? That's what this left-hand side is. It's effectively a sequence of numbers that you would hope converges to the integral of f, right? So if the sequence of functions converges in this way, you then, so the authors say, you would hope that the sequence of integrals would converge in a similar way. Now, it is kind of my opinion that this is not motivating, at least not for me. I don't, I know that some people are motivated, and I don't suggest that there's anything wrong with being motivated by these things, but I can only speak from my own personal subjective experience in feeling like these things don't motivate me. I look at, the fact that, we cannot integrate certain functions like the Dirichlet function and think, well, I'm not sure that we should integrate it. And even if we should, then I'm not sure why this even matters at all. Then there's, why would I want to integrate functions which are not functions of a real variable? I mean, I just kind of honestly don't. Not honestly, because like at this point in my education, I do know which functions I would like to integrate, which are not of a real variable, but they're not easy to describe at this particular moment. So, so I know that like when I was initially learning this material, I did not realize like, why would I want to integrate some function that is not a function of a real variable? Like I just I don't have a kind of context that would help me to understand why that matters. And then further, why would I want completeness? I mean, it might seem like maybe some kind of nice idea or nice result, but again, I'm just kind of lacking the sort of context that would help me to understand why I should want these things at all. So I found these motivations when I first encountered them somewhat unmotivating, but there is something that does motivate me. And what does motivate me is the history, which I know, maybe I'm a little bit, unusual in this way. I think like a lot of people find the history of mathematics somewhat, idle and uninteresting and does not help to motivate anything for them. But for me, it does. I mean, in my eyes, I'm really looking at like, real problems, right? So real that they really existed in the past. And, we're watching, by reading history and understanding what people were doing, we're actually seeing people who were confronted with such an unavoidable problem that they had to spend years inventing theories to overcome them. And so that is, at least in my personal opinion, more compelling. And so because that is compelling to me, then I am going to try to sort of talk about that in the next video. And that means that I need to go beyond the textbook and use a resource, which is this Wikiversity page. And so I'll be, showing you that in the next video and talking about it. I'm going to try to keep it brief because I know that these motivations are not really necessary for everybody, but it certainly matters to me. So I'm going to at least talk about it for one video, and I'll try to limit it to that.